I'm Jack Burke, editor of CompressorTech2 magazine, and thank you for joining us today for this, what I hope to be a lively discussion about LNG. Before we officially get started, I want to give viewers a few more moments to log in so they don't miss anything. All right. Once again, I'm Jack Burke, editor of CompressorTech2 magazine, and thank you again for joining us for this podcast. Today, we're discussing one of the most dynamic sectors of the natural gas industry, liquefied natural gas. Global LNG demands continue to grow, driving new investments in liquefaction capacity, export infrastructure, and the technologies that support efficient, reliable operations. Joining us are two experts with deep experience across the LNG value chain. Mary Beth McBain of Siemens Energy brings decades of experience in compression, rotating machinery, and LNG technology, while Mehdi Tool offers a global perspective on liquefaction systems, plant operations, and emerging industrial trends. In this episode, we'll explore the technologies, operating challenges, and market forces shaping the next phase of LNG development and what they mean for project developers, operators, and equipment suppliers worldwide. I'd like to let our audience know that at the bottom of the screen, there's a Q&A button, so please feel free to ask questions as the podcast goes along, or the webinar goes along. Right now, I'd like to welcome again Mary Beth and Mehdi. And Mary Beth, would you like to begin your presentation?
Yes, thank you, Jack. And thanks to all the viewers and listeners for calling or logging in this morning or this afternoon, if it's in a different time zone for you. And also, I am, I guess, honored to represent Siemens Energy this morning. Thanks to the folks at Siemens Energy who also helped prepare me for these slides. Definitely slicker slides than I would be able to come up with on my own. So let me just share those with you all to get started here. And just to kind of give everyone an overview of where we're headed, we didn't want this to just be about myself speaking. So I have about 10 slides prepared, and hopefully that won't go longer than 20 or 25 minutes. And then we wanted to have some Q&A with Mehdi's thoughts and his experiences in terms of what's next for LNG. So we'll open it up to Q&A about midway through this webinar. I'll provide a little bit of commentation, but I think that'll mainly be Mehdi. And then we also want to allow some time at the end for sort of live Q&A. So once again, the Q&A button at the bottom, feel free to type in your questions or comments with questions, and we'll try to take the ones that are most popular as we go through this. So hopefully everyone can see my screen okay? Great. So this morning, we're talking about compression solutions for LNG. A lot of time and attention gets spent on the process, which is very important, and a lot of times on the drivers, the gas turbine, which you see here, or the motor drives. But I'm happy that we're focusing on compression here. It's CompressorTech2's webinar, but it's sort of my passion for the last many decades is compression. So that's the part of the equipment right here on the right. So that's a mixed refrigerant compressor with a gas turbine driving it. And that's what we're going to kind of speak on today. So let's see if I can get onto the next screen. So we want to kind of talk about what's next for LNG. America's experiencing a large LNG boom, given our great resources in natural gas and project development efforts here. But it's also globally become a fuel that helps us decarbonize and is available in many locations around the world. Also provides for energy shortages in other spaces where oil might be limited, or as a backup for renewables coming onto the grid. Natural gas being the perfect intermediate fuel there. So in terms of a size trend, we're seeing more development in this 2.5 to 3.5 million tons per annum size. And Mehdi may comment on this and disagree, but there was an emphasis on sort of these mega projects in the 10 to 12 million ton per annum range. And some of those got to FID and are under construction or operating now. But in some ways, this size is a lot more nimble and agile, trying to get to the 80% offtake volume in terms of being able to make FID. You can always add expansion if the site permits at a later date. But this seems to be a size that works really well with being able to get to market sooner. And agility matters more than ever in this sort of new age of LNG. This size also fits well with a variety of LNG process options. So the single mixed refrigerant sort of being a popular one right now, but also the C3MR process by Honeywell AP, and dual mixed refrigerant processes by a variety of licensors. And they can also work in this size scale where they gain those economies of scale over once you get into that larger range above the 2 million tons per annum. So this lends itself to being centered on multiple 40 megawatt type SMR trains, or going with the larger, different, more complex cycles, which can fit into a 60 or 70 megawatt train size. And again, this is doable now with LNG, motor driven, as well as gas turbines. And there's some merits to both, and we'll speak on both of those today. And, this is also sort of the new days of LNG, where, you go back and look at Turbo Machinery Symposium papers, which I've done, and very well written by experts in the industry. But when they were talking about LNG, the technology has changed so much in the last really 10 years or 5 years, where we see references in larger horsepower class for variable frequency drives. And that's sort of the key enabling technology that we needed to get to where we could do motor-driven LNG. Because we had motors and we had generators that are basically a motor design way over 100 megawatts, but we needed those VFDs to be able to give us references. But in the old days, the majors dominated the industry, and they sort of had the ease of longer construction timeline because they were already in the LNG game, trading LNG, and being able to realize gains from those past projects. And now we have a lot of new actors and players in the industry that are able to make this happen as well. So that sort of gives variety. It also means that we can look at customization and ways to optimize the process. And that's one thing that we do really well as a partner with an operator, realizing that each project is different. So different environmental drivers, air emissions profiles are different around the globe. The US is more relaxed on that now, but other spaces in the world are not. So that might drive towards more of an LNG design, depending on how much renewables are on the grid and if you can really make the case for a lower carbon signature. We also have different marketability of LNG in different locations and availability of gas. The Gulf Coast is getting more constrained. We're getting pipelines built as fast as we can, but that is different than it was 10 years ago in terms of how much gas is available in those locations. Another interesting trend we're seeing on the gas side is nitrogen content. So in the US, pipeline tariffs are usually limited to 3% total diluents. And that's a combination of your nitrogen, CO2, and other non-BTU gases. And traditionally, nitrogen was below 1%, and now it's sort of creeping up there, which is an issue for how you're making LNG, how much nitrogen you're going to get in the boil-off gas, whether you want to put an NRU in. So all this lends itself to really being able to partner more closely with OEMs and understanding how to truly optimize a plant. So, the example of having higher nitrogen in the boil-off gas, that might mean, hey, we can take that gas, we can burn it in our turbine because we have a turbine that goes up to 50% nitrogen on the fuel. And then you can use that for power, but you want to make sure your process is optimized for that full power range so that you're getting all of that power at the refrigerant compressor and making it into LNG. So it's even more essential for that close partnership with the OEM on the optimization side. So just quickly highlighting in a very simplified way, the LNG process, maybe for those who are less familiar. I'm not a process engineer. Mehdi's probably way more schooled in this than myself, but just to kind of highlight where we see compressors in an LNG plant. So we always talk about the heart of the plant right here in the middle, and that's the liquefaction space. And that's where you have your process, and this one sort of highlights more of like a C3MR type style, where you have a propane pre-cooler and refrigerant compressors, mixed refrigerant, and a coil wound heat exchanger. But this could also be an SMR process or dual mixed refrigerant. But beyond those compressors, on the pre-treatment side, you typically have a feed gas booster compressor and possibly a regeneration or acid gas recovery unit that involves compression. And this pre-treatment is very customized to the type of gas that you have coming in. So, other places around the world, maybe the Middle East is closer to the upstream. So that nitrogen content might be very high for certain upstream fields, or higher amounts of heavier hydrocarbons. So this is typically very customized to the site and the gas feed on the pre-treatment. And then we run through liquefaction. The gas flows against the refrigerant in the heat exchanger and becomes liquefied natural gas. Option is to add the cold side NRU when it comes off of the gas comes off of the liquefaction module, and you can run this through a distillation column to drop out the nitrogen. However, some plants don't have that and take the gas directly to the LNG storage. And then you have usually a boil-off gas compressor, or a bank of boil-off gas compressors, where the gas is loaded onto tankers, but at the same time, parts of it vaporize. And nitrogen is a part of that, as well as things that drop out quicker. And it basically just the surface temperatures itself. So that boil-off gas is essentially like wasted LNG, but typically is taken back to fuel or recycled back to the process. And we've highlighted here areas where we see opportunities to make this even more a low carbon LNG process. And that's sort of shown here. We don't have time to go into that today, but would love to talk to y'all about that later. So in terms of eLNG versus turbine drive, one of our best references on eLNG is wood fiber. Currently under construction, it's a 2.1 million ton per annum project, British Columbia, and it uses the C3MR process. So it's entirely motor driven, with a large portion of the power coming from renewable hydropower in that area. So this gives us a very marketable low carbon LNG, and Siemens Energy provided all of the motors and the drives and the electrical equipment along with the compressors. So a pretty interesting reference because it's pushing up into that horsepower class. And we'll talk about a little bit more of the process, but it's a good model for other projects which are looking for a low environmental footprint, especially when you have some renewable power available in the area. Contrasting that, we have gas turbine driven compression. So our SGT 750 is the main driver on reference project Delphin for floating LNG. It's designed for 4.4 million tons per annum with the single mixed refrigerant processed by Preco by Black & Veatch. And in general, gas turbines have been sort of the bread and butter for the LNG projects. To date, there were a couple steam turbine driven ones, maybe back in the late 60s and 70s, but everything else has been driven by gas turbines. So, the ability to purely operate your plant on the natural gas by itself gives it huge flexibility. So onshore or fully offshore. This particular project, Delphin, is a floating LNG project. So it's a little more challenging in terms of wave and wind loading. And we'll talk a little bit more about that, but lends itself really well to being able to put those gas turbines on the floating rig. The SGT 750 has its maximum mean time between ovals in its class, and its optimized speed at 6,100 RPM fits really well with the mixed refrigerant compressor in that size, at like the 40 megawatt size for the mixed refrigerant compressor. So that allows you to do direct drive, no gearbox, cutting out that additional amount of loss in the efficiency of the drivetrain. So this was an excellent project. We'll talk a little bit more about that in the coming slides. So for focusing back on the electric EMD LNG compressors, with wood fiber, we had kind of two configuration options, and it actually went with this bottom one here because this allows you to put two of the compressors on the same drivetrain with one motor, and then a similar sized motor for the LP mixed refrigerant. So propane and HP mixed refrigerant on one drivetrain, and then your LP mixed refrigerant compressor on the other motor. Both sized for around 47.5 megawatts, and that's at 105% full speed, full load. So when we did all of our acceptance testing with wood fiber in Duisburg, we had some different acceptance criteria that lends itself to eLNG compared to gas turbines. So we're definitely testing all of the compressor performance as we normally do in Duisburg, but we're also testing the motor and VFD side of things, because that's where we really want to mitigate risk and give complete assurance for eLNG. So we did a full 4-hour full load VSD and motor test. We had the job transformers, the job variable speed drives, the e-houses, the motors, the compressors. That was the, as much of a full string test as you could possibly get. And along with that, we were able to test our converter temperature rise within the variable speed drive, input and output waveforms, measured overall efficiency, and also took measurements of the power factor and what was going on with some of the harmonics and interharmonics. We chose LCI type variable speed drives, so that's a current source inverter drive, which normally needs some type of harmonic filter. So that's why we wanted to make sure we were getting the right interharmonics and damping of those harmonic waveforms as part of our risk mitigation testing. So this was all a complete success and shipped to site, so underway on construction there. In that eLNG space, it's also interesting to note that there's a number of options for process control. So variable speed drives, you'll need them in some way to start these large motors. But there's other ways to do a soft starter without buying a full load VFD. And that might be appealing to some, especially if you wanted to do process control with inlet guide vanes. And that's one thing that we have a lot of experience with at Siemens Energy, with variable inlet guide vanes to control the flow through the compressor. That's the picture shown here, where we're basically affecting the angle of the incoming flow. This would sit at the inlet to your first impeller on the centrifugal compressor, and basically give you huge amounts of turn down capability at relatively high efficiencies in a mechanical way, as you can see, by affecting the inlet guide vane angle of the flow. And this is kind of a contrast to the electrical way of doing process control with VFDs. So both are options. On boil-off gas compressors, we use variable inlet guide vanes routinely, and offer a fixed speed operation without the need for a VFD on the boil-off gas compressor. So there's no reason that can't be done on a mixed refrigerant as well. And you can see sort of on the right side some of these other processes, how that would look with motor-driven compression. The single mixed refrigerant process is a single compressor with direct drive or gearbox and motor. And then we have dual mixed refrigerant with two different embodiments here, when you can kind of combine and do a 2x50 design or 1x100 design for both types of refrigerant blend that you need. And then finally, the C3MR process, which is the one that wood fiber has selected for their project. And then just really quickly, kind of highlighting again some of that string testing that we did with wood fiber. A picture down here of the Duisburg string test, the mega test facility that we have there. And a lot of the electrical equipment is not shown, the e-houses, the transformers, and the VFDs, but that was also included in this string testing. And I could talk a long time about this, so I won't, but happy to give these slides to anyone that would like. That current source inverter versus the voltage source inverter. That's the big question if you're going to go with the VFD style of process control. And both have some pluses and minuses. Overall, you're looking at a similar overall footprint when you include the e-house and harmonic filters of an LCI drive versus not having all of those on a VSI drive, but typically more power modules for those inverter requirements when you're converting the waveform back to the speed for the motor. So these are all, both types are water cooled typically when you get above 10 megawatts, and water cooled drives have their own water cooling loops, but it's another thing that you want to test in your string testing to verify that cooler performance, because these are going to want to get really hot. Okay, so then moving on, last couple minutes here, gas turbine driven LNG. So we're also very excited about gas turbines and the full capabilities of the SGT 750. Typically in these processes, it equates to one SGT 750, ISO rated 42 megawatts in ISO conditions, and around 38 megawatts for your hotter ambient conditions. And that one SGT 750 gives you about 1 million tons per annum for your LNG. And so you can keep scaling that up. And when you go into more of these a little more complicated cycles, you get a little bit more efficiency out of that. But in general, that's sort of your nominal nameplate capacity. And your shaft efficiency on an SGT 750 at ISO conditions is around 41.7%. So I think that's industry leading efficiency for this type of turbine. Again, I mentioned the RPM for the power turbine at 6,100. That can be direct driven to the compressor. And our NOx emissions are at 9 ppm. That's without any after treatment or anything going on with your stack. That's just the pure DLE combustion system. We also have a lot of fuel flexibility with this engine, being able to take the higher nitrogen content. So that gives you some capabilities, and maybe you don't want to put the NRU in, take all that boil off gas back, burn it as fuel, make it into power, maybe some flexibility in that way. And finally, just to highlight the Delphin project. So this is a gas turbine project, 2 gas turbine driven MR compressors in a single mixed refrigerant process. So that's nice and simple going on to a floating LNG rig. This is an extremely impressive project by Black & Veatch using their Preco single mixed refrigerant process. The location was just released, I think, recently in the last couple months for offshore Louisiana and the Gulf of Mexico. So that's kind of interesting because Black & Veatch started working with us in the early phases where they were designing without a specific site. Well, I mean, for as much as I know, a specific site location in mind. And that means being able to conservatively estimate the wave and wind loading so that the design can be generic enough that it would work at multiple sites offshore, depending on what those conditions would be. So when we started working with them, there was the early engagement needed for, okay, where to locate the gas turbine driven compressor packages in terms of maintenance access, crane capacity, being able to access that, as you can see on this complicated floating LNG rig. And then once that sort of space study was done, we also started on our dynamic FEA analysis. And this is the most critical for our compressor equipment. And it's not just about the nozzle loading. We're also looking at, low cycle and high cycle fatigue, low cycle being your startup and shutdown conditions, and high cycle fatigue being the additional wave and wind motion that is added on top of how you're running. So that affects nozzles, casing, base plate, instrumentation panels. All of that has to be analyzed in your dynamic FEA study and designed appropriately. And ultimately, there's sort of a give and take in the end of, hey, we've done the best we can, and we still We need a little bit more from the process piping in terms of the loads that it's bearing and not imposing on us. So it's very much a partnership with the designer. And that's one thing that we were really proud of in getting this project to a successful state. So the units will be shipped by Samsung and built in the shipyard there, and then final commissioning will be offshore in Louisiana. So I think then I haven't gone over too much, and we can kind of go into somebody else getting to talk here for the webinar, and I'll turn it over to Jack and Mehdi.
All right, thank you very much, Mary Beth. Very interesting information. One of the key things I took away from that is how important it is to have those early conversations. In the LNG process, Mehdi, what should developers be looking at, and what should they keep in mind first?
Yeah, thank you. Thank you, Mary Beth, for the insightful presentation. Good morning, good afternoon, and good evening, everyone, wherever you are in this world. When it comes to discussing the liquefaction selection for the technology, it's very important to. I would say I was a culprit of considering the technology selection as the most important factor to take into account, and that the liquefaction license that you would go to would represent the main cost driver for your liquefaction project. However, I discovered thanks to my good friend Don Hill, a legend in the LNG industry, that this is not the case. A project and a successful energy project is framed and defined by external factors that you need to look at before looking at the technology selection and the compression solution. You need to look at your market first, of course. The location, we have seen that in the US. Location is equally important. You need to look at the labor cost. You need to look at the permitting process or regulatory frameworks available in your region or your country. All those parameters will define your technology selection. And of course, from a cost perspective, major concerns, especially in the US, is the workforce and labor cost and expertise. But going back to my background as an operator, if you ask me, as an operator, what would be my preferred liquefaction technology? Of course, I have my own preference. You would go to an EPC contractor. Maybe they have existing strategic partnerships with given licensors, and they are more comfortable proposing that to you as a developer. But I think, like Mary Beth mentioned in her presentation, it's very important to focus on early engagement and all the involved parties, and to bring in early on the operational feedback from existing facilities and share from across the industry to avoid repeating mistakes. Some processes have been operating for decades. They are very well known. The level of expertise and talent available in the industry is quite significant. And there are new processes equally promising that are taking more market share right now that we still need to learn and be familiar with. But it's really key to have all the actors involved early on during the development phase, and have the OEMs, the developers, the operators all together defining the best technology depending on the condition, and the best operating strategy for the future. Because constructing and designing a plant is something, but operating it for over a couple or 3 decades and more, it's a totally different animal.
All right, thank you.
Welcome.
As an observer of the industry, one of the things that I noticed is that electric drive seemed to have a lot of interest a few years ago. Is it more of a trend, or is it more of a fad right now in the LNG segment?
Yeah. So there have been recently a lot of talk around the full electrification of LNG facility, LNG projects. I think the first wave was really pioneering the LNG configuration. We learned a lot from that first wave of projects. I think there were some issues related not to the technology we deployed or the equipment deployed from within those facilities, but it was mostly related to a grid integration issues and understanding of the impact of the grid stability on the LNG process. So I think that now, especially on the motor side, no, I'm sure Mary Beth, you agree with me. Today, electric motors, are almost a commodity. But when it comes to aligning all the VFDs with the right compression solution with the given type of motor is the key to a successful LNG project.
Yeah, absolutely, Mehdi. I agree with you. There's a lot of different options to consider in terms of LNG VFDs that weren't available before, and how that works with your motor and VFD manufacturer. But then integrating with the grid is maybe one of the most important critical for success factors. So making sure that that design is done in cooperation or with a partner group that has that capability for grid assurance, power and correction of power. And some of these sites, tend to be more island style without the grid needs. And some of them are integrated more with the local grid, and some type of renewables build out. So like I said, it varies all over the map. And that's another reason why the early engagement is critical.
Yeah, and with the rise of data centers and power plants being deployed in the US, you need to have a really forward-looking vision on the evolution of the grid. The grid is evolving rapidly, and you need to adapt to that, and you need to be ready because you can have all the best harmonic, and you look at all the conversion factors of your equipment. If you don't predict how the grid will be in the next 10 to 15 years, you will be in trouble.
Yes, yes. I had the ability to sit in on a session that was very interesting about a year ago in one of these energy storage conferences given by a professor in Spain, speaking about what happened when Spain
Yes.
had the blackout. And it was, kind of, I mean, I'm not an electrical person, but, there's a lot of renewable wind turbines in Spain, and they don't have a lot of rolling generation kind of backing that up. And that, I guess, correct reactive power got really out of whack. And so obviously, there wasn't an LNG plant affected in that area, but you can envision that's, something to kind of think about for future in terms of how the grid is changing.
Yeah, absolutely. And I want to say something that when you hear an LNG facility tripping or having trouble, don't blame the facility itself. Look at the grid and the grid integration. Yeah.
I think that's a good point because the pace of the change of the grid and the power demands, especially from data centers that are coming up, is just going to be hard to gauge looking forward. I think anyone that's going to be looking to develop one of these facilities is going to have to really have a long-term perspective. Speaking of low carbon LNG, we've got many variations. What is most likely and most feasible for development?
Yeah, low carbon LNG. I like the term. We saw the industry moved away from after many years from the carbon neutral LNG term that I didn't like much because we have to be honest with ourselves. It's a fossil fuel industry, so we need to embrace that first. When it comes to low carbon LNG, we need to look not only at the liquefaction side of the supply chain, but at the wellhead as well. And I think from a carbon abatement strategy, this is the key factor that you need to look at. Start by reduce your methane intensity at the wellhead, then look at other solutions which are already available and they have been proven in the market. So the immediate solution, of course, is to be energy efficient. And that goes back to shaft power integration with your given and selected liquefaction technology. But there are also other solutions that are costly, mainly carbon capture and storage and sequestration. So I think that the carbon capture systems have evolved rapidly. A lot of lessons learned from the LNG industry. not always successful, but again, it is not a blame on the technology itself. It's a blame on the integration and the impact of external factors. So I think if you are nearby an oil field and you have carbon CO2 pipeline available, that's a great solution. You can utilize that capture carbon from the acid gas removal unit for enhanced oil recovery. That's a very economical solution. Also, you need to look at subsidies available in your region, your country. It depends. That could help alleviate the cost of deploying such solution. I think we are still really far from adopting, capturing carbon from combustion. It's a very costly way of reducing our emissions. So I think there is a lot to be done on the technology on that side. But again, it's all about efficiency across the supply chain. It's not only the blame on the liquefaction facilities. It's about reducing flaring. It's about better BOG management. And again, it takes you to machinery as well. So I think it's all about being more efficient in how you liquefy and transport your gas.
Yeah, I think that's a really good point, Mehdi, is that we still need to focus on energy efficiency. And so lowering the amount of flaring, boil off gas management, making sure that we're sized correctly for taking full boil off gas and keeping those compressors up and running as a mitigation. And I think it's important to also take credit for, baby steps. We might not all be completely, 0% CO2 emissions, but taking the right steps towards that goal. So like your solution with the acid gas recovery unit, being able to take the CO2 and all the nasties that come out of that acid gas recovery and take that to some type of CCS, either reinjection or liquefying it to CO2 and then disposing it. I think that's an easy one to start on. And then we work ourselves into more and more lower carbon signatures.
Absolutely.
Yeah, that's right.
Mary Beth, you discussed the Delphin project, and that looks like a immense project and very complicated. Can you talk about some of the difficulties or the differences between land-based and floating LNG projects?
Yeah, so I think Delphin is a great example of some of the complexity, but then being able to meet those challenges and deliver a gas turbine driven compressor and all of the additional compressor auxiliaries, the boil off gas, the booster compressors for that floating rig with the wave and wind motion of a floating platform, either platform or this is actually a true floating vessel. So those projects are a little bit obviously more intensive on the engineering side on the upfront. But the nice thing about that particular project is, as I mentioned in my remarks, it was sort of generically designed in the way that it was conservatively designed for the range of anticipated conditions you might see, which means that now we have a design and a partnership that we can market to other projects. And Black & Veatch was an excellent partner with us, and I think they had that kind of vision as well. So it's like everything with technology. We're taking the steps, we're meeting the challenges, and the success is there. So that's the reference. And so then it really takes off after that because you've proven it. It's still, I think, a dynamic project space in terms of the many versions of offshore that we might see. There's sort of the near shore barge that doesn't have nearly as much motion as a true floating vessel. And then there's sort of the platform, which is maybe nearer to shore as well, but has additional space ramifications. So I think we're going to see a lot of those type of projects take off when we get these references in place.
Yes, one of the things that impressed me the most when I visited a shipyard developing one of those solutions in China, I was really impressed by the complexity. So we had early on during the very first phase of development of FLNG projects, we had the impression that those projects were flexible, nimble, agile, and easy to, like almost a kind of a plug and play projects, but this is not the case. Highly complex, they have to answer to a lot of restrictions. On the machinery side, I had so many questions about vibration, about lubrication, and it's not easy deploying an FLNG asset. You cannot repurpose it to another field if the composition is different. So I think we'll see now it's being dominated by SMR technologies variant, mainly the Preco from backend Vich. But if you go to if you want to upscale and be more energy efficient, I think we will go into the DMR territory more, and we have seen that in Mozambique. And I think that is going to increase in the future. There are still very few FLNG projects being developed. Most of them, the new ones, and the ones that are still at the proposal level, they are more of the nearshore type, like you described. But I think that we change in the future because we are getting a lot of feedback from DMR operations.
And with DMR, you have, I guess, the lower amount of stored inventory, so lends itself nicely in terms of offshore.
Yeah, it's critical because from the safety aspect, so you get rid of the propane inventory on board. So it's a big bonus for any offshore application, of course.
NRU integration, is that something we'll see more of? What kind of optimization angles are there in that?
Yeah, that's the issue of nitrogen, and you covered that briefly during your presentation, Maribeth. The issue of nitrogen is not new. There are other fields globally that face that issue early on, and they were designed to that. In opposite to the US, so now we have an issue that in the Permian Basin, especially the gas coming from Midland, nitrogen is increasing because this is the characteristic of developing a shale gas well. So you get a lot of gas initially, then it declines quite quickly. So you move to the next one, and it comes with different nitrogen content. So the easiest way of controlling that is, of course, relying on blending solutions. So blending low nitrogen gas with high nitrogen gas, but it's not always an issue, especially with the next wave of LNG projects. They are connected to a single pipeline, so they don't have the ability to blend gas. And you need to look at how to handle that increasing nitrogen from a design standpoint. Of course, the easiest way, if you have a gas turbine on site for power generation or others, would be to use that methane-rich nitrogen that you will recover from a very simple end flash gas after liquefaction. You can use it for fuel, although that comes with limitation of the type of turbine that you will be using. Like you mentioned, some have a limitation how much nitrogen they can burn. But also you need to look if your nitrogen, so the maximum you can go with from a liquefaction standpoint is 1%. You cannot go above 1% in your final product. So a simple end flash gas system would reduce that by half. So you would be, if you have 2% nitrogen in your feed gas, using a simple end flash gas system, you can lower that by 1%. So it's still okay from a heating value for your customers, and also to avoid any rollover phenomenon in your tanks during loading in the ship. But also, and it's very important from a compression standpoint, nitrogen in your feed gas will increase compression duty. So that takes us back to the efficiency. So if you have a nitrogen-rich gas, you will spend more kilowatt. So you will increase your specific power to liquefy that gas. So there is nothing much you can do upstream if you don't have any blending facility. But what you can do on top of the end flash gas system, and you don't want to keep recirculating the nitrogen from boil of gas to the tank, and from tank to your liquefaction facility, because nitrogen will build up in the loop. So that's not a solution. So what you can do is add an NRU. There are multiple variants available in the market. So it depends on purity of nitrogen you want to recover. So it depends also on from a permitting standpoint, it depends on the region you are at, because you will have a limit on how much methane you are allowed in your nitrogen, even if it's high purity in a nitrogen stream that you can release to the atmosphere. So that there might be other uses for that nitrogen, but NRU comes with a cost, so it will add cost to your overall tolling capacity. and you need to consider that. And from a compression standpoint, also the compressor that you will use will have a very high compression factor, because nitrogen, LNG is flashed at a very low pressure to recover that nitrogen. So you will go from maybe close to atmospheric pressure to a high discharge pressure. So you need to factor in your compression selection as well into that.
Yeah, that's right, Mehdi. So that's an area where we've designed a number of compressors for NRUs where you sort of have like an LP stage, and you boost the gas coming in to the distillation column. And then on the exit, as you mentioned, high ratio compressor casing that, mini impellers that handles that amount of pressure ratio you need for the basically very low inlet pressure to get back to the fuel pressure or whatever you're going to do with the gas coming out. But I will say that with the economics as they are right now, sometimes it's pretty beneficial to look at putting in an NRU, because you can take the higher nitrogen gas, which is unmarketable or less marketable and offered at a discount, put in the NRU, and then when you're able to make more LNG out of that gas with the NRU there, then you're paying back for that NRU in very record time with the current LNG prices.
Mm-hmm. And now the issue we are facing for LNG facilities, that once you remove any BOG consumer from site, so your largest BOG consumer would be your gas turbines. So if you remove your gas turbines, now you are facing a trouble, because you don't have where to take that BOG. It might contain a lot of nitrogen. So, and the BOG generation is changing in nature. Whenever you have a ship loading, you will need to subcool your LNG to reduce the amount of nitrogen that will flash in your tanks, and that's really another constraint to the deployment and the selection of LNG facilities. That's I think BOG management was already an issue for gas turbine driven LNG plants, and it will become more of an issue for all electrified LNG facilities.
Yeah, good point.
Well, let's talk a little bit about the boil-off gas compressors. How are they sized, and what criteria determines how many you need at a site?
Yep. So we are probably the market leader in boil-off gas compressors, and these are usually like 2 casing designs, because again, it's also a high ratio where they're coming off at the boil-off gas at atmospheric pressure, and taking it back to either make more LNG or likely to the fuel for the plant. So typically they're critical because you want them always to be running, whether or not you're doing ship loading or not, you're still having a boil-off gas amount of flow coming off of the tanks. And since there's a lot of variation in how the flow performs because of the ship loading operations, and that's not always a constant, they need a lot of turn down. So typically we size those with our inlet guide vane system, because we're able to really exploit huge amounts of turn down at a low cost with the mechanical inlet guide vanes on that first casing inlet section. And then certain operators might want to also buy the 2+1 design, so we're offering 3 identical designs of that boil-off gas compressor.
Yeah, it's also part of your flaring strategy and emission reductions. If you don't size and you don't plan accordingly your sparing strategy or your redundancy strategy for your boil-off compressors, you might end up flaring more. I have seen that in multiple facilities that were not, they didn't take into account the type of ship they would be receiving, hot ship, cold ship. It will all impact your BOG and your BOG recycling. And if you don't size your compressor accordingly and prepare for the redundancy plan accordingly, you will face a lot of trouble, and sometimes you will be forced to flare, and that will impact your whole baseline of flaring across the year.
Yeah, and then that's back to, hey, how low carbon do you want to be and energy efficient do you, because that's a big waste to be flaring.
Sure.
We have yet to see IGCC compressors deployed for refrigeration in large-scale liquefaction facilities. Why do you think developers are reluctant to use them?
So we went over, in the slides that I presented, the many different types of compressors in the plant. And I think there's only really two areas where you see a very high pressure ratio needed. And so that's the number one reason, is that IGC compressors are really only something you would want to consider when you have a high pressure ratio. At least this is my opinion. And others may beg to differ. And another point is that why fix something that's not broken? So mixed refrigerants with single shaft have been increasingly gaining on the highest, most advanced aerodynamics for the impeller designs, and for that entire compressor being able to deliver something above 87% efficiency on its aero design. So being able to take that to the IGC space, there's a lot of question marks. And beyond that, typically, even though IGCs can be made very reliably, and we make IGCs reliably, if there is an issue, an IGC will have a longer amount of downtime. So it's not like a 1 or 2 day usually repair timeline. It might take longer than that with an IGC. That's a disadvantage. But as I mentioned, there are advantages and different applications where IGCs make sense as well.
From from my very humble operator opinion, I hate IGCs. Yes, like you said, when it comes to maintenance and the seal gas system, you need to prepare accordingly. And like you said, maintenance can take a lot longer. And I faced issues in the past with the fuel gas compressors from the flash gas applications in LNG trains. And I won't say it was a nightmare, but it took a lot of our time and attention. So I think that the pushback is really from an operation standpoint.
What about high-speed direct drive?
That's a big one as well. So that's a big one. I know, I don't know why, but from the operation community, we got used to gear the ratios. So I don't know where is the pushback coming from for high-speed drive and direct drive. So I would love to hear your thought on that, Maribeth.
Well, I think high-speed electric motors have gained a lot of ground in the last 5 years. I mean, it's impressive. So I think, they're even pushing up towards like 20 megawatts. That's to say they're still at 20 megawatts as far as I know. So, most of these mixed refrigerant type compressors, as we saw, 40, 60, 70 megawatts for LNG plants. And I just don't see high speed motors getting to that power size anytime soon. There's also the concept that, you're saving the gearbox, but the gearbox, a well-designed gearbox, is maybe 1% inefficient at most. So, I mean, it is a little bit, and every little bit counts in LNG, but, the gains aren't that much for a lot of risk. And the reason that they, are struggling beyond that 20 megawatt mark on high-speed motors, I think, is the heat management. There's a lot of heat generated, and they've got to be able to manage that, just like basic physics says. So I don't see them solving those issues to go into bigger power class in the near term.
Yeah, and there is also a size issue. So if you have a limited footprint, especially on FLNG applications, so you want to reduce the overall size of your compression string as much as you can. So of course, removing the gearbox, that would be ideal.
That's true, yeah. And I mean, that's back to IGCs, are a bigger footprint typically, because you have a lot of interconnected process coolers after every stage, and basically the multi-pinion gearbox. So in terms of footprint, your single stage compressors are going to be the smallest. I see some questions coming in regarding reciprocating compressors, and I think that's a great question, because in some areas of the plant, recips have been considered, and in others not. So on the booster side, a lot of times that will go into a recip selection. Reciprocating compressors are going to be a more comparable option for lower power signatures, typically I would say below 10 megawatts, and pressure ratios that are pretty decent, above.
Sorry, Mary Beth. Sorry,
yeah.
You meant reciprocating engines?
Yeah. So recip
Okay.
engines with a recip compressor or a motor-driven recip compressor. Yeah, that's right. So, those also tend to have a bigger footprint with pulsation bottles and the attached kind of auxiliaries. But I think, on the front end of the plant at the booster side, we have seen reciprocating compressors used there. But then back to the power issue on your heart of the plant refrigerant compressors, you need these really large power classes. So I don't see that going to recip compressor anytime soon.
Okay.
That's correct. Yes.
Or anytime at all.
Okay, so yes, we have some time for a few questions from the audience. We talked a little bit about why the preference for turbines and electric motors as opposed to reciprocating compressor or reciprocating engines in the LNG space. Yes, we will be sharing the slides. I will be able to place them on our website, I do believe, as if that's all right, Mary Beth.
Yes, I think so.
Here's a very specific API question. Why are API 617 centrifugal compressors dominant in the LNG while API 618 recips are limited to niche services?
Yes. So I think that's similar to what I was kind of alluding on that last comment in that, API 618 recip kind of process compression. If you wanted to spec a recip compressor for an LNG plant, you would do it on the booster side in that sort of inlet stage to your pretreatment area, because there you need a pressure ratio and typically of maybe, it depends on the size of the plant, but some of those are less than 10 megawatt in size. So there you would want to have the reference to API 618, given the criticality of an LNG plant. A lot of pipeline compressors are not necessarily API 618. They're just recip compressors designed to a certain pipeline compressors operators spec for the manufacturer. So 617 centrifugal compressors, both single shaft and IGC, are pretty much more common throughout the LNG plant. And I really only see the API 618 recip compressors on the booster side because of that pressure ratio and lower power required.
I'm trying to see.
There is a very interesting question. So in the LNG industry, do you have any reference regarding the conversion of turbo compressors to engine-driven compressors?
Yeah, that's interesting. So Mehdi, you have probably more experience than me for sure on the variety. And I think, so the question is probably asking a motor-driven turbo compressor.
Yeah, turbo compressor, so
to...
replacing gas turbine-driven compressor with an electric motor. There is only one example that comes to my mind is the Arctic LNG2 project in Russia as a result of sanctions. So they removed the existing gas turbine, replaced them with large, I think it was 75 megawatts motors. But I cannot comment on was it successful or not. We don't have data on that. But that was an extreme case. I don't think that we'll see that in the future. That would require a major redesign efforts to do that. And I don't see it commercially attractive to undertake this kind of change or swap.
Yes, I would agree.
Yeah.
I think we have maybe time for one more question. I guess, what are the major compression challenges in the Louisiana project?
So I think they maybe are alluding to the Delphin project, which I covered. Yeah,
I would think so.
And yeah. So I think, when they found that project location, the gas had been secured in terms of feed gas and being able to fit the profile of what Delphin was designed for. So I think that was, at first a challenge in being able to align, the gas mixture for pipeline gas coming into Louisiana and to secure the volumes. And then on the compression side, just in terms of a floating rig, it did require the upfront sort of homework and a lot of great engineers in Duisburg and Houston looking at this and designing for all of the additional robustness that you need in the base plate, in the casing, and in the nozzle loads. And so we were very happy to have a partner that we were working with in Black & Veatch that we could kind of have some give and take on the process piping being able to manage how we design that base plate for both the gas turbine and the compressor side, because all of the different reactive loads affect each other.
Okay. Mehdi, Mary Beth, before we close, any final thoughts that you'd like to share?
I just wanted to say thanks so much to both CompressorTech2 and Siemens Energy and Mehdi. And I do apologize if I was a little loud with the background air conditioning here in my house. Someone made a comment about that, but hopefully they stuck around for the rest, and I turned it off. So I'm just getting a little hot. But
That was a compressor, yes. That was a compressor, of course.
A not designed, not well-designed compressor.
Thank you for the opportunity and for the exchange. Really insightful for everyone, and a lot of learnings, and looking forward to another opportunity. Thank you.
All right. Thank you both, Mehdi and Mary Beth, and to Siemens Energy for helping sponsor this webinar. And thanks to the audience for again, I'm Jack Burke, editor of CompressorTech2, and have a good day.